Hello everyone, I'm Xinru Wang. Today I'm glad to present our work, Human-LLM Collaborative Annotation through Effective Verification of LLM Labels. This work was done with my dear mentors Hannah, Zhengjie, Sajjadur and Kushan at Megagon Labs during an internship. In today's world, the rapid progress of machine learning heavily relies on the availability of abundant annotated training data. Traditionally, humans did all the labeling, which can be costly and time-consuming. One way to speed up labeling is by leveraging machine pre-labeling. Large language models, which have impressed us with their excellent performance in many tasks, have also shown their skills in labeling data. While a fully automated data annotation process using LLMs would significantly reduce the annotation cost, the performance of LLMs substantially varies across datasets, and they may even introduce biased outputs. Therefore, LLMs cannot fully replace human annotators. Instead, we should leverage the strengths of both LLMs and humans. The question then becomes, how can we effectively utilize LLMs as collaborators for data annotation? In this work, we propose a multi-step Human-LLM collaborative framework for data annotation to ensure the accuracy and trustworthiness. In this framework, we first use LLMs to generate labels on unlabeled data. Then, we verify the quality of LLM's annotation. Finally, human annotators re-annotate a subset of labels selected by the verifier, which avoids wasting human effort on correcting already accurate labels. Now, our Human-LLM collaborative framework was inspired by two lines of work. The first one studies how to verify the uncertainty of LLM responses. In the literature, LLM confidences are approximated using logic-based self-evaluation or self-consistency methods. However, LLMs are often overconfident, or some methods may incur additional prompting cost. Instead, people have shown that training a separate simple verifier to re-rank LLM's outputs with the help of pre-extracted features from the example to annotate and the corresponding LLM output is effective. Another line of prior work that can enhance this data annotation framework is to leverage the LLM's capability to generate self-explanations. In the verification step, those explanations could provide more information on the LLM's reasoning process for the verifier to distinguish incorrect LLM annotations. On the other hand, in the re-annotation step, explanations can help human annotators to understand and trust LLMs as collaborators. To build such a framework that effectively combines the strengths of LLMs and humans through explanation and verification, in this paper, we explore the following research questions. First, how to verify LLM-generated labels using signals from inputs, LLM labels, and LLM explanations. And second, does providing LLM-generated labels and explanations help humans in re-annotation? Let's begin with the first research question. In the first step of our proposed framework, the LLM generates labels for input samples and provides corresponding explanations. In our experiment, we sample three general-purpose text classification tasks: natural language inference, stance detection, and hate speech detection. For each of these tasks, we select two representative datasets, and for each dataset, we randomly sampled 2,000 examples for evaluation. For example, natural language inference is the task of determining the inference relation between the hypothesis sentence and the premise sentence, and the table on the right shows our prompt template. We use GPT 3.5 to annotate each dataset and to obtain explanations. Then we develop a verifying model which assigns scores on the quality of LLM-generated labels. The resulting scores help identify a subset of potentially incorrect LLM labels to be re-annotated by humans. Specifically, the LLMs takes text input as text samples as the input and generates labels and explanations as the output. This allows us to consider signals from 3 dimensions along the LLM annotation process: the input sample, the LLM-generated labels, and the LLM-generated explanations. This gives us a total of 70 input features, 7 label features, and 73 explanation features. Let me describe a subset of features to you. Readability indicates whether it's hard for humans to understand the task. The logit of the label tokens measures the uncertainty associated with the GPT label accuracy. And higher coherence score refers to better logical connections in the text. We can implement the verifier using any binary classification model. Here let me show you the evaluation results using random forest. Also, training the verifier would require a few gold labels. We consider a setting that we believe are reasonable in practice. The verifier is trained on a small set of 500 examples from the same dataset, plus 2,000 examples from different datasets in the same task domain. The rest 1,500 examples were used for testing. Assuming that the bottom examples ranked by each verifier to be re-annotated by humans, the accuracy of verifier for bottom 100, 200, and 300 examples shows that no verifier better identifies incorrect LLM labels than logit-based baseline. Now let's move on to our second research question. Does providing LLM-generated labels and explanations help humans in re-annotation? In this step, human annotators re-annotate the subset identified by the verifier model in the previous step. In practice scenarios, the re-annotators may not always provide accurate labels. Thus, a human subject study involving real human annotators becomes necessary. To understand what's the optimal strategy for enhancing human re-annotation performance, we adopted a within-subject design and created 3 treatments by varying whether and how the LLM assists human annotators with the re-annotation. In the non-LLM assistance treatment, participants are not presented with any output from the LLM on each data instance. In the LLM label treatment, participants are presented with the label generated by the LLM. And in the LLM label and explanation treatment, participants are presented with both the label and the explanation generated by the LLM. As illustrated in this figure of the task interface, for each data instance, participants review the data instance with or without the LLM prediction and the explanation, and then provide a final annotation. We selected 2 re-annotation tasks, SNL dataset for the natural language inference task and SAM-EVOL dataset for the stance detection task. For each dataset, we selected the bottom 20% or 300 instances with the lowest scores from the verifier for participants to re-annotate. In the experiment, participants first completed a demographic survey. They then proceeded to annotate a set of 30 data instances divided into 3 phases with 10 instances in each phase. Each phase corresponded to one of the 3 within-subject treatments: non-LLM assistance, LLM label, or LLM label and explanation. Note that for each participant, the order of LLM assistant treatments was also randomized. Before exit, participants were also required to complete an exit survey, where they were asked to report their perceived annotation experience for each phase. We launched our study in Prolific. To be practical for annotation tasks, each instance was annotated by 3 human annotators. Looking into the results, we found that the instances where LLM was correct, participants were more accurate with more LLM assistance. In contrast, when LLMs was incorrect, providing the wrong LLM labels hurted human accuracy, and there were no differences between showing both the LLM explanation and label and showing only the LLM label. We also analyzed the exit survey ratings on participants' self-assessed accuracy. For the SNLI dataset, the self-assessed accuracy of participants was higher for LLM-assisted treatments. In contrast, for the semi-evolved dataset, participants believed that their accuracy was higher when only labels were given, compared with when both labels and explanations were provided. Upon further examination, we found that the quality of explanations generated for the semi-evolved dataset was lower. For example, there were more explanations in the dataset with lower coherence scores compared with in the SNLI dataset. To summarize, our results show that our verifier trained with LLM-generated explanations can achieve much higher accuracy than baseline methods, which means that different signals can be informative when verifying LLM labels. The crowdsourced human study tells us that there's a need to quantify and improve the quality of LLM explanations and carefully decide when explanations are helpful for human re-annotation. That's all about our study. Thank you for listening.